Welcome guys. In this video I will tell about the electrochemistry and the very important cyclic voltammetry. Basically, cyclic voltammetry is very important in electrochemistry. So before start to the cyclic voltammetry, I would like to share the detail about the electrochemistry a little bit, the very basic fundamental about electrochemistry as well. For example, that electrochemistry is basically the study of current or the transfer of electrons and the study of the resultant product which come into being because of the electron transfer. So it is basically the probe or investigations of the process which come in resultant as a resultant of the current passing through the electrolyte and the resultant product which come into being. So for example, in this case, we will study a little bit about the ferrocenium as an example, and this is the cyclopentadienyl is represented by Cb. So ferrocenium is Fc actually is a oxidation form which reduced to the ferrocene shown by Fc. So in this example, where Fc plus is given, so it means that it is ferrocenium, while where Fc is given, so it means that is ferrocene. For example, in this process, ferrocenium has electron deficient, so it get electron from this Cp, cyclopentadienyl, and it get reduced to the Fc by getting one electron from this. So the ferrocenium get reduced to the ferrocene, while this Cp oxidized to the COC2 plus. This shows that it lost electron. So in electrochemistry we have three basic things. For example, and the one is the working electrode, the one is counter electrode, and the third one is the reference electrode. We will study about this. The working electrode is basically the very important among these three. Uh, Actually, the whole reaction is taken by these working electrons, and it provides the required electron to the species for the reactions we will study later on. So the next one is the counter electrode. Counter electrode is the opposite of the working electrode, and remember that on working electrode basically reduction occur, while on the counter electrode oxidation occur. It's mean that on working electrode the species uh, gain electrons, while on a counter electrode the species lose electron. While the reference electrode is given in the cell in order to measure the specific potential which is supplied by the external battery to this uh, working electrode. So there are different type of a reference electrode can be used, like SCE and like standard hydrogen electrode. So these type of electrode can be used as a reference electrode in order to measure the correct potential supplied to the working electrode. For example, in this case, the HOMO, we call that HOMO, high occupied molecular orbital of this Cp is higher as compared to the ferrocenium low occupied molecular orbital. So that's why the electron transfer easily from this Cp to this, and it become fulfill this orbital of ferrocenium become fulfill, and it become reduced to the ferrocene. It become to the ferrocene, while the Cp lose one electron which was present in the reactant, so it become to the plus. It oxidize and this one reduce. The same case happens in the electrochemistry as well. when ferrocerium, for example, when the ferrocerium get attached to the electrode, so the electrode energy is made higher by the external supplied potential to the electrode, because of which the higher the higher occupied molecular orbital energy of this electrode become higher as compared to the ferrocerium. So then the electrons transfer from the electrode surface become easier to the ferrocerium, and it get reduced to the ferrocene. So there's become oxidized and there's become reduced. That is the phenomena which occur in electrochemistry. That is why we supply external potential to this electrode in order to increase the higher occupied molecular orbital energy, in order for the easier transfer of electron from this electrode to the species, any species. In this case we have ferrocerium. So, and the higher occupied molecular orbital energy is basically controlled through the potentiostat, which is attached to this working electrode. The next one is the cyclic voltammetry. After getting the enough knowledge, basic knowledge of electrochemistry, we come to the cyclic voltammetry. So cyclic voltammetry is a very important terminology uh, which is used in electrochemistry in order to probe the activities of species which is occurring within the electrochemical cell, that what is happening in the electrochemical cells. So for this process, the cyclic voltammetry, actually the cyclic voltammetry give us instantaneous informations about the species which is present inside the electrochemical cells, that what is happening, either there is the species concentration is reducing with the passage of time, and the another species concentration is increasing with the passage of time, and what happened when we move toward the negative low potential, and what happened to the move when we move high potentials, and where the oxidation occurs and where the reduction occurs. All these information is given by the cyclic voltammetry. Cyclic voltammetry has actually many forms, like square wave voltammetry, like linear saturated voltammetry, blah blah blah. I am planning to make another video on these voltammetry as well. The representation of the cyclic voltammetry has two types. For example, one is US convention, and with the reduction peak. The reduction peak is upward while the oxidation peak is downward, as shown here. We can see that. While the IOPAC mm, convention is the reverse of this US. So we will focus on this US convention methodologies, and I will try to explain in more detail with the further example. For example, in order to get the detail about this, so in this case we can see that this is the concentrations. The blue line is showing the ferrocerium, which is start. So this shows that at the start, when E is equal to E1, they are talking about this at the start. There, look at that, this figure A dash. At the start, when potential was equal to E1, so there was only ferrocerium, mean that Fc plus was only present at the surface of the working electrode. So as we started to supply the voltage, increase the voltage towards negative, we see that as we are moving toward the B, what happened? Look, come to this figure. The concentration of ferrocerium on the surface is increasing, and as we move toward the bulk concentration mean that away from the electrode. So as we move away from the electrode, as the distance increases, the ferrocenium species concentration increases, and after a certain distance from an electrode it becomes constant. So the same thing happened with the ferrocene amount. The green line shows the ferrocene at that point B. When E is equal to E half at point B, the ferrocenium and the ferrocene amount on the cathode is equal. But as we move away from the cathode, so the ferrocene mean that Fc is decreasing away from the cathode, while the ferrocenium Fc plus is increasing up to certain limit. Therefore, further increasing the voltage, we come here to this highest maximum point, point C. So the concentration at this point at this point C, at point C of the peak, the concentration of ferrocene, which is Fc plus, is now lesser than the ferrocene. We can see that the ferrocene is having higher concentration value, while the ferrocenium is having lesser concentration value on cathode. So as we move away from the distance from the cathode, the ferrocene concentration is now decreasing again, while the ferrocenium concentration is increasing after certain distance, while it becomes constant onward. This diagram is showing this point of the graph, and after then further decreasing, further moving toward the negative applied potential, and we reach to the point D. So in this case, at the point D here, we can see that the ferrocenium here is totally become zero on the surface of the cathode, while a ferrocene is having the highest maximum value at the cathode, which shows that all the Fc plus which was present highest at the start at point A is now have been converted to the Fc. This means that at point A, this Fc was the maximum value, while at point D, the whole Fc has gained electron and now reduced to the ferrocene value. We can see that at point D, the ferrocene has the highest value and the ferrocenium has the lowest value. So as we move away from the cathode, so the amount of ferrocene is decreasing and the amount of ferrocenium is increasing, because near the surface of cathode there are only ferrocenium, but there is a diffusion layer of ferrocene. But as we move away from the cathode, so there are other ferrocenium which can't reach to the surface of cathode. So this is called diffusion layer. So from point A to point D, this whole path is called cathodic trace, that is represented here. Point A to point D, we are increasing the potential like this. So this path is showing the cathodic trace, and in this graph it is shown here. So this is the cathodic path. When the whole ferrocenium is converted to the Fc, now then it reverses back through this way, and when it reach to the point E, now what happens happens that at point E, the amount of ferrocenium, this and the amount of this, become equal on the surface of the cathode, as it is shown in this E. Look at that. Concentration of this green, which is Fc, ferrocene, and the concentration of blue, which is ferrocenium. Both are same at the cathode surface. But as we move away from the cathode surface, the amount of ferrocene is decreasing and the amount of ferrocenium is increasing. So that is shown here in this, when the potential become half of potential. This is called formal standard potential of a species. Each species has value. So now moving toward the point F, as we increase further positive potential to the working electrode, what we see that now here come to the point F, the amount of ferrocenium is higher now. Again, now shift. The amount of ferrocenium at the cathode is higher than the amount of ferrocene. It means that the reactant is again higher, and this is lower on the surface. Further moving toward the G, we can see that the whole amount is again on the surface. The maximum amount is the ferrocenium, back this Fc plus, and there is very less amount of this Fc. It means that this is a reaction get back to the Fc, oxidize back, and this path is shown, the point from point D to from G. This path is called anodic trace, and it has been represented in this graph from D to G. Now it is worth noting that this IPC, that is called maximum current peak of cathode, and this peak is called maximum current of anode. You get this point? And this, the difference between this and this is called change in potential. This is called change in potential. For a single electron transfer, it must be 57 millivolt. It must be 57 millivolt. While this peak value is basically directly related to the scan rate. Now, what is scan rate? We will discuss later on in this video, and all these diagrams can be shown by can be represented or explained by the Nurnus equation. So Nurnus equation is very basic equation which is shown here. Nurnus equation is basically relating the cell potential E to the standard potential E of the species. This R is universal gas constant, T is the applied temperature, N is the number of electron transfer to the species in an electrochemical cell, and F is the periodic constant, which is having a value 96485 coulomb per mole, and log of activities mean oxidation divided by reduction. If we convert this natural log to the common log, so we get this constant value. We can also replace this oxidation and reduction of the species with the ferrocenium concentrations and ferrocene concentrations. So it's mean that we can find the electrochemical cell potential by knowing the value of formal potential. What is formal standard potential? This shows that the formal potential, which is represented by E1/2, and this shows the formal potential, anodic potential, which is represented by E/2. That is common for anode and cathode. So this is formal standard potential, and we know this universal gas constant, all these constant, and that is the concentration of ferrocene plus ferrocene, oxidized form and the reduced form. So by knowing all these, we can find the E, or by knowing E and E, we can find the concentrations. Nurnus equation also shows that what happens to the concentration of species when we change the E. So now what is the next important thing is the scan rate. Scan rate is actually shows the cyclic volt per second applied to the surface of cathode. The higher the scan rate, we can show that from here, this V is scan rate. Actually, Randall-Sevick equation describe the behavior of peak current with the scan rate changes. So this Randall-Sevick equation shows that this is the peak current values. Peak current, which I already discussed, this is peak current value. So this shows that the Randall equation shows that how this peak current value behave by with changing the scan rate. So this is the scan rate. Again, this is the geometric surface area of cathode. C is basically the concentration of a species. N is the number of electron. All these things. D is the diffusivity coefficients, centimeter square per second. So this, from this equation we can say that the peak current is directly proportional to the square root of scan rate. So as we increase the scan rate, so we will get the a higher amount of peak current, and the other in the other values, in the other value, I will show that what is scan rate and how it can affect our electrochemical performance. So thank you for your watching. Keep watching and please subscribe our channel if you learn. Thank you for watching.